We've been aware of fossils and their significance as messengers from the past for quite a while now. At times their interpretation may have differed quite radically from our understanding today, as you can see in this wonderful rendering of the ancient oceans of England by Henry de la Beche. But paleontology is a dynamic, ever-changing science. It's one of the reasons I love it. Paleontology as a modern science is a relatively new discipline with its roots in the European Enlightenment of the 18th century. At this time, reductionism, an approach to understanding nature by reducing it into smaller, simpler parts, and scientific rigour were hot intellectual movements of the day. It was in this environment that paleontology and geology would grow and become sciences in their own right. It's from early pioneers like James Hutton here that we get much of the common core of the way we practice the science today. However, as a discipline, paleontology has not stood still, and new technologies and techniques have pushed the science forward, particularly in the last 30 years, with ever-increasing speed. So in this episode, I'd like to consider some of the tools and techniques used by paleontologists and how new technologies are opening up windows into the past in a way that would have just astounded the founding fathers and mothers of geology and paleontology back in the 18th century. So let's ask, how do you find fossils in the field? How do we collect fossils? How are fossils prepared? What are the new tools of the trade that we can use? And look at how we can breathe life into fossils through scientific illustration and reconstruction. Many, but not all, paleontologists were first trained as geologists before specialising in the study of fossils. That was my background. There are many very good reasons for this. In part, an appreciation of geology helps place fossils in the context of a dynamic Earth system, which in turn has implications for the way in which we interpret the fossils we find. But also, a paleontologist has to rely on a number of basic geological principles and skills in order to track down and accurately record the fossils they find. In particular, there are principles regarding the manner in which rocks, sedimentary mostly, are deposited one on top of another over time. These ideas basically state that the sequential deposition of sediments means that the oldest layers or strata will be at the bottom of a pile and the youngest at the top. Now, this is not rocket science, I'm sure you'll agree, but it is a fundamental concept if we are to read these strata and the fossils they contain, like peeling the pages back of a book. As geologists, we know that our dynamic planet rarely allows for the thin crust we live on to stay still for very long. Horizontal strata, more often than not, will become tilted and folded over time as continents wander, collide and raise mountains, twisting and distorting the geological pages of Earth's history book. This can complicate matters when we are trying to read Earth's story, which is why a vital skill for any paleontologist or geologist out in the field is the ability to create and read geological maps. Geology is very rarely beautifully exposed like you see here in the Grand Canyon in Arizona. The story we want to tell is often covered by a soil profile, vegetation of some sort, asphalt, or an inconvenient shopping mall. Paleontologist is often only presented with a fragmentary glimpse of the geology at the surface in the form of limited outcrops with little evidence of what the geology is doing in the subsurface. It is from these limited views that geologists create a map, a hypothesis of both the seen and the unseen below the surface. Even though aerial and satellite photography and gravity and magnetic surveys can help with mapping today, the geoscientist still has to rely mostly on getting down on the ground and hiking around along the outcrops of rock. Like the first geological map makers, such as William Smith, who produced the really first large-scale geological map, the basic equipment of geological hammer, hand lens, compass with a clinometer for measuring the dip of strata and a notebook to record your findings is still the basic kit in the field. GPS and an electronic data storage device are certainly used, but any geologist worth their salt should only need the basics and just a little bit of hard work. When complete, the map is tested. After all, a geological map is basically a hypothesis based on what is often incomplete information. It is tested by continued mapping, or in some cases by drilling boreholes to see if your subsurface predictions are actually matched by the rocks you recover in core. Predictions that might be confirmed by characteristic rock types and/or fossils, for example. In this way, the geology of an area, especially when those areas might be geologically complex, is revisited and refined, tweaked, so that the model we produce comes closer and closer to the reality of the rocks in the earth. A good geological map can help a paleontologist predict the location of strata of particular interest across the landscape, with fossils themselves tying those strata into a temporal framework. A map, therefore, can help a paleontologist zero in on the pages of Earth's history that they are interested in, and also helps that paleontologist understand the wider temporal context of the fossils that they find. Even though a map may help you focus in on an area you should be looking for fossils, there may still be a lot of hunting around to find the fossils once you're in the field. A good start is to eyeball the ground for fragments of fossils in what we call float. These are loose pieces of rock that have been eroded from an outcrop that actually contains the fossils you're looking for. This was how Smithsonian Secretary Charles Walcott zeroed in on the fantastic fossils of the Burgess Shale by first finding loose specimens in a scree slope. A scree slope is a loose rock debris flow, and carefully tracing them upslope till he and his family found the now famous fossil-bearing strata in Walcott's Quarry, a beautiful area of the world if ever you get to British Columbia. In the same way, during July 2000, Neil Shubin and his colleagues investigating strata on Ellesmere Island in the Canadian Arctic would track down fragments of bone to a bluff, which in Shubin's word were kicking out bones. Some of these bones would be one of the most significant fossils of recent times. Tiktaalik, a fish that was on its way to becoming a land-based tetrapod, a transitional form, that is, a fossil that is partway between one type of creature and another. It's basically a fossil that is showing that evolution happens. But what about collecting the fossils once they've been located? Well, this will vary depending on what fossils you are finding, but for most, like the shells of various marine creatures, fossils can often be collected by the application of hammer, chisel, crowbars, and just a little muscle, making sure your eyes are protected by safety glasses, as many of the rocks will have a high silica content and splinter into dangerous shards when hit. Once recorded, the fossils are wrapped to protect them placed in a bag with an identification number. This, of course, becomes a little more tricky when dealing with something like this. Wrapping this in a copy of the National Enquirer and stuffing it in your backpack isn't really an option, and sometimes a small pick and a hammer just aren't going to be enough. And that's when you might see the field paleontologist employing a jackhammer or a backhoe, probably grinning with absolute delight. In addition, it is generally impractical to extract large fossils from their rock matrix in the field, so once the specimen has been exposed, it is extracted with the adjacent rock material still attached to the fossil that you're interested in. Plaster and burlap straps are then applied to the specimen, forming a kind of a jacket, and once hardened, the fossils can be removed and transported back to the lab. Sometimes, given the remoteness of the sections being studied, this could require a helicopter, and another opportunity for a happy paleontologist to indulge their inner 6-year-old. My own experience of collecting fossils has been a little different though. As a micropaleontologist, I don't have the luxury of seeing my fossils in the field as much as I really would have liked to at some times. Most microfossils are fractions of a millimetre in size and often impossible to see, even with a powerful hand lens when you're out in the field. The best we can do is find the right kind of rocks that might, just might, contain the fossils we're looking for. For example, the microfossils I study, the Chitinozoa and the planktonic forams of Dr. Brian Huber of the Department of Paleobiology, are exclusively marine. Of course, the right age of rocks is vital too. For my Chitinozoa, that ranges from the Lower Cambrian period, about 510 million years ago, through to the end of the Devonian period, about 359 million years ago. That spans some 151 million years of the geological record. After that, we just have to sample the strata and hope that we find the fossils when we get back to the lab. Oh, please. Of course, it does have the advantage, if conducting fieldwork, particularly in the United Kingdom, of allowing micropaleontologists to be the first back at the pub after a day in the field and not worrying about spending days of labour excavating a large and troublesome dinosaur. But common to all fossil collection is recording as much detail as possible regarding where the fossils were found, not just spatially, but also stratigraphically. So we're not just plotting them on the map, we also need to know their vertical time extent, as well as their lateral geographic relationships. This is why fossils collected illegally by fossil hunters have much less value scientifically, especially as context is so important when considering the specimens that are recovered. If removed from their contextual setting, a fossil loses all of the associations that might be able to be drawn from all the other information that might be included in the rocks from which they originally were found. To this end, and to preserve both their original geographical and stratigraphical location, fossils are often recorded on a stratigraphic log. A strat log, as we often call it, is a vertical representation of strata that are being studied. They are often depicted like this: a vertical set of rocks that you might find exposed, for example, in a quarry face or in cliffs along a coastline, even if the rocks themselves in outcrop are tilted or folded. Such a vertical column just makes time-based arrangements of fossils just easier to understand and interpret. Back at the lab, in the case of the larger specimens, the fossils have their plaster jacket removed, and the long and very careful process of removing the fossils from the rock matrix will begin. A number of tools are used for this, including the air scribe, which acts a bit like a miniature jackhammer chipping away at the rock matrix. When getting close to removing the majority of this matrix, the air scribe's impacts may actually pop off the last bits of rock, leaving fossils beautifully clean and exposed. If that doesn't happen, it's time to break out picks and needles, removing remaining matrix grain by painstaking grain. If a fossil is too fragile or the matrix is too hard, fossil preparators may use gentle grinding tools to help separate them from the rock. Once again though, when getting close to the fossil, it is only tiny picks and needles that are used to clean up the specimen. As you can see, a steady hand and a lot of patience is required for this job. Various adhesives are an essential part of a fossil preparator's toolkit as well. Thick solutions can be used to rejoin large broken fragments of fossil. For fragile specimens, a thin solution can be applied that penetrates into the cracks and pores, strengthening the fossil from within. After a fossil is rejoined, they are often placed in sand that holds the pieces in the correct position until the adhesive sets. When complete, spectacular detail can be revealed. Detail like you can see on fantastic reconstructions of dinosaurs, or in the beautiful and delicate spines and processes that have been uncovered from these exquisitely prepared trilobites released from their rocky matrix after hundreds of millions of years. As we noted, with regard to collecting specimens, the preparation of fossils at the other end of the scale with microfossils is somewhat different. The most common method of preparing microfossils involves the use of various, often very nasty acids, such as the hydrofluoric acid that I had to use in my research to extract my Chitenozoa. In this way, you're able to dissolve away the rocky matrix and reveal the fossils. Once you have them, you have to concentrate the residue of material up. And then once you have that concentrated residue, spread them onto a microscope slide or pick through them using fine brushes, bristles or fine pipettes. After all the exciting collection and preparation of your specimens, there is another stage that needs to be completed, whatever type of paleontologist you are. The fossils need, in fact, must be curated. This is often one aspect of paleontology that is overlooked by the media, which is unfortunate, as curation of material, safely storing, recording and documenting is vital to the science. If we did not have dedicated curators at museums and universities, all we would have are rooms full of undocumented fossils slowly falling apart in dusty drawers and cabinets, of little to no use to science. The National Museum of Natural History currently holds over 126 million items, and counting. Samples ranging from fossilised pollen to bones of Tyrannosaurus rex, samples of algae or slabs of a giant sequoia tree, tiny crustaceans to giant squids, insects trapped in amber, and samples of DNA, the skulls of whales and the dung of ground sloths, the Hope Diamond, and rocks from the moon. What a wonderful palace of treasures this is. But let's consider now some of the tools we use to study our fossils. In Robert Hooke's famous publication of January 1665, Micrographia, a whole new world was revealed, the world of the very, very small. Hooke's beautiful drawings, such as these of the flea and the compound eye of a dragonfly, were instrumental in promoting the early use of the microscope in understanding the natural world. Hooke would also turn his attention to fossils through his study of petrified wood, in observing that structures he found in petrified wood very closely resembled those he could see in rotten oak. He concluded that wood would be turned to stone if water percolated through its tissues, precipitating minerals. Since then, microscopes have been used in many branches of paleontology for studying various aspects of fossils, commonly by making a thin section of the rock that reveal the internal anatomy of well-preserved fossils as light passes through them. In this magnified thin section of an Ordovician limestone, the scale bar here is about 2 millimeters, you can see a fragment of a trilobite and spine from an echinoderm, a sea urchin. Optical microscopy has its limitations though. Practically, you have a maximum magnification of about 1,500 times due to the wavelength of light that limits the resolution of the microscope. In addition, there is a problem with depth of field in viewing specimens that have much relief, such as, for example, an entire trilobite exoskeleton. As such, optical microscopes essentially provide a flat image. Fortunately, we can use something other than photons of light to make images of the very small. In 1924, Louis de Broglie postulated that beams of electrons behaved in a manner similar to beams of light. As such, it would be possible to produce a microscope that used electrons rather than photons. In addition, as electrons have a much shorter wavelength than light, they would also have much greater resolution. This idea would be taken forward by Max Noll and Ernest Ruska during the 1930s, who, by 1935, had constructed the first crude scanning electron microscope, or SEM as we call them. By 1965, the Cambridge Instrument Company produced the first commercial machine, and SEMs have been an important part of many paleontologists' toolkits ever since. Basically, an SEM is composed of an electron gun which fires a beam of electrons into a vacuum chamber. A vacuum is necessary as electrons don't travel very far in air. The electrons are often generated by heating a metal filament, commonly tungsten, as it has a very high melting point. These electrons, being negatively charged, are then attracted to and accelerated by a positively charged electrode or anode. Rather than glass lenses, the electron beam in an SEM is focused by electromagnetic coils, and then the beam moved from side to side by another magnetic coil, such that it scans over the surface of the object being studied. Some of the electrons get absorbed by the object, which then emits electrons back to the SEM, while others get reflected or backscattered. The electrons are collected by detectors, and the specific pattern of electrons received used to help resolve a detailed image that's displayed on a monitor. The resolution of an SEM is far greater than an optical microscope and can range up to around 300,000 times. This is why they are often placed in the basements of buildings due to the sensitivity of instruments to vibrations, such as, for example, heavy truck traffic passing by a museum or a university. To increase magnification, the microscope just scans over a much smaller area of the object. An image is built through repeated scans, row by row, producing a more three-dimensional image when compared to the flatter images of optical microscopes. SEMs have another trick up their sleeves though. Some of the electrons fired at the object travel deeper into the specimen, get absorbed and cause a release of X-rays. These X-rays can then be used to determine the composition of an object being studied. All you need is an SEM fitted with an X-ray detector. This technique, called Energy Dispersive X-ray Spectroscopy, or EDS for short, has been used recently in a research team headed by Conrad Labandera at the National Museum of Natural History. Conrad and his team were looking at exceptionally preserved material in Middle Jurassic and Early Cretaceous lake sediments in northeast China. The fossils they found include insects in the order Neuroptera, the group that modern lacewings belong to, that appeared to be taking on very butterfly-like habits by visiting plants for nectar about 40 million years before butterflies evolved. One of the fossils, Orogramma illosabrosa, even possessed eye spots, very similar to modern owl butterflies that use them to trick predators that a large animal is nearby. The eye spots of this insect were analysed using EDS. EDS relies on the fact that each element emits characteristic X-rays when excited by a beam of electrons in an SEM. As a result, EDS allows for the composition of a specimen to be determined. From this analysis, it was proposed that these Jurassic lacewings were using the chemical melanin to create their eye spots, just like modern butterflies do today. We have other tools for determining the composition of materials though, and in some cases determining the relative proportions of very specific isotopic components of a material can provide vital environmental information about the past. An isotope is a variant of an element that differs only in the number of neutrons it contains in its nucleus. Some of these isotopes are unstable and decay into more stable elements over various time periods. Others are stable and hang around in the environment. For example, consider two isotopes of the element carbon, carbon-12 and carbon-13. Carbon-12 is by far the most abundant, comprising around 98.93% of all elemental carbon. Carbon-12 has 6 electrons and in the nucleus 6 protons and 6 neutrons, thus giving us an atomic mass number of 12. Carbon-13, however, has 7 neutrons in its nucleus, giving it the higher mass number of 13. So what? Well, importantly in nature, different stable isotopes of elements get preferentially fractionated by differing processes over time. For example, in the case of carbon-12 and its heavier sister isotope carbon-13, carbon-12 is preferentially used by living things. This means that proportionally, there will be a higher concentration of carbon-13 in the general environment as a lot of carbon-12, the lighter isotope, is being concentrated by living things within the biosphere. During events such as a mass extinction, the uptake of carbon-12 gets severely reduced, flooding the environment with more carbon-12 and diluting the carbon-13 isotope. an important isotopic signal of past crises in the biosphere. It's not just carbon though. Isotopes of oxygen, sulfur, nitrogen, and a whole bunch of others react in very specific ways to different environmental factors that speak to various events in Earth's past, some of which we'll examine in this series. To obtain these isotopes though, we need a very specific piece of equipment called a mass spectrometer. The substance you want to study gets placed in a vacuum chamber and then is bombarded with electrons. This knocks ions off the sample and transforms them into positive ions. These are then accelerated towards a negatively charged plate and the ion beam passed through a magnetic field. The lighter ions, such as carbon-12, are bent further than the heavier ones, such as carbon-13, creating an ion spectrum that can be read on a detector. Mass spectrometers are used in another regard too, but this time using unstable radioactive isotopes. When a radioactive element decays, it emits radiation and is transformed into a different, more stable element. This is called radioactive decay. Each radioactive isotope has a specific and constant rate of decay from the original parent material to the stable daughter product. The rate of decay is described by the half-life of the isotope. That is the time it takes for half of the parent element to decay into the daughter product. For example, potassium-40 decays into argon-40 with a half-life of about 1.25 billion years. That means that after 1.25 billion years, half the potassium-40 in a rock will have become argon-40. If a sample contained equal amounts of potassium-40 and argon-40 therefore, it would be 1.25 billion years old. If the sample contained 3 atoms of potassium-40 for every 1 atom of argon-40, it would be 625 million years old, and so on. It is usually igneous rocks that are used in radiometric dating. Igneous rocks form as magma or lava cools, forming crystals that trap small amounts of radioactive material. This can then be used to calculate the age of the rock. This technique has permitted the dating of materials from many periods of Earth's history, including some of the most ancient. For example, Earth's oldest rocks from northern Canada, the Acasta gneiss, dated to about 4 billion years old. Moon rocks, dated at around about 4.4 to 4.5 billion years. And meteorites, basically debris left over from the formation of the solar system, dated to 4.4 to 4.6 billion years. We will look more at how we date rocks and fossils, including using radiometric dating, in another episode of this series. Although I've included SEMs and mass spectrometers under new tools, they've been around for quite a while. There are now many new techniques, though, that would have appeared incredible even when I started my PhD back in the 1980s. Much of it related to advances in computing power and innovations in instrumentation. An example currently being used at the Smithsonian Institution involves capturing precious fossils in 3 dimensions on a computer. The digitization program at the Smithsonian can capture incredible detail from a specimen using millions, sometimes billions of points of measurement on its surface. These wonderful pictures were provided by Conrad Labandera at the museum and are X-ray computer tomography images of a mite and a pseudoscorpion trapped in Baltic amber. The power of digitization has also been demonstrated recently by Smithsonian paleontologist Nick Pianson, who uncovered a fantastic fossil site in the remote Atacama Desert of Chile. In 2010, a construction crew widening the Pan American Highway exposed a remarkable whale fossil site. Nick had to document and move these fossils in a hurry before the area was paved over. The whole site was captured digitally by technicians from the Smithsonian Institution. To find out how they did this, catch the lecture on whale evolution later in this series. Just because we have new technologies available to us, though, doesn't mean that we abandon more traditional tools. This is nowhere better seen than in the power of paleontological art and illustration. Science meets art when we need to reconstruct ancient environments and the organisms that lived in them. The Smithsonian has a rich history of paleontological art. In 1995, dinosaur collections manager Michael Brett Sermon discovered a set of approximately 1,200 illustrations of dinosaur skeletal material on top of a specimen storage cabinet. What he found were beautiful ink-washed drawings that had been prepared for the famous paleontologist Othniel Charles Marsh in the late 19th century. Even with all the wonderful new advances in imaging and data manipulation, the role of the scientific illustrator, like Mary Parish in the Department of Paleobiology, is still vital both in research and in public display of materials. Very often an illustration can highlight features that might be too subtle to be picked out on a photograph, and also correct for problems such as poor depth of field or distortion that can occur with a camera lens. Paleontologists require a wide variety of visual materials to illustrate their work, including the reconstruction of fossil specimens, restorations of ancient animals and plants, and various diagrams, graphics and maps to help illustrate research. Often drawings reveal structure, anatomy and features that are not really grasped in photographic images. For me though, it is the collaboration between artists and scientists in the reconstruction of past environments that I find the most inspiring. The reconstruction of paleo-environments begins with consultations between artists and paleontologists, perhaps with the scientists making a rough initial sketch. From materials such as specimens, photographs and a range of other background material, the scientific illustrator begins to bring to life lost landscapes and the animals and plants that populated them. The result is the point where art and science meet to produce wonderful images such as this, breathing life into worlds long since vanished. This image, and others like it, are the product of all that fieldwork, preparation, analysis and interpretation that is part of the wonderful science of paleontology.